47 years ago, humanity sent a machine into the sky with instructions to never come back. It flew past Jupiter. It flew past Saturn, Uranus, and Neptune. 4 planets visited by a single spacecraft, a feat never attempted before or since. Then it kept going, past the last known boundary of our solar system, into interstellar space, into the cold dark between stars. And it is still transmitting, still sending signals home across a distance so vast that the signal itself takes over 19 hours to arrive. And what scientists are now decoding from those transmissions, from data that has taken nearly 5 decades to collect, is forcing a complete rethinking of what exists beyond the protective bubble of our sun. Not a small revision, not a footnote in a textbook. A fundamental rethinking of what interstellar space actually is and why it behaves nothing like the empty silence we assumed it would be. Voyager 2 launched on August 20th, 1977, 16 days before its twin Voyager 1. It took a slower, curved path through the solar system, using the gravity of each giant planet like a slingshot to accelerate toward the next. Jupiter in 1979, Saturn in 1981, Uranus in 1986, the first spacecraft to ever reach it. Neptune in 1989, still the only spacecraft to have visited it. At every stop, the data Voyager 2 sent back rewrote what we knew about those worlds. Active volcanoes on Jupiter's moon, heliopause, geysers of nitrogen on Neptune's moon, Triton. Magnetic fields tilted at angles nobody had predicted. But all of that was just the warm-up. The real story began much later, on November 5th, 2018, when Voyager 2 crossed the heliopause and became the second human-made object to enter true interstellar space. The heliopause is the boundary where the sun's reach ends. Inside it, the solar wind, a constant stream of charged particles ejected by the sun, fills all of space, pushing outward against the interstellar medium. At the heliopause, that outward push exactly balances the pressure of the interstellar wind flowing inward from the galaxy. It is not a wall. It is more like a shoreline, a dynamic boundary that shifts and flexes with the sun's changing activity. Voyager 1 crossed it in 2012 and sent back data that raised immediate questions. But Voyager 1's plasma science instrument had failed decades earlier, leaving a critical gap in its readings. When Voyager 2 made the same crossing 6 years later, with its plasma instrument still functioning, it handed scientists something priceless. A complete, direct measurement of exactly what happens at the edge of the solar system. And what they found there changed everything. The first shock was the boundary itself. Voyager 2's instruments showed that the heliopause crossing happened in less than a single day. A boundary that separates the interior of the solar system from interstellar space, a transition spanning the largest structure humanity has ever measured, resolved itself in under 24 hours of the spacecraft's travel time. IT was sharper than any model had predicted. Not a gradual fade from solar to interstellar conditions. A sudden, decisive edge. The plasma inside the heliosphere was hot and sparse. The plasma in interstellar space immediately outside was cold and dense. The jump in density was approximately a factor of 20, happening almost instantaneously as the boundary crossed. Scientists looking at the data sat quietly with it for a long time. Nature is not supposed to produce edges that clean. Then the temperature readings came back, and they were wrong. The very local interstellar medium, the region immediately beyond the heliopause, was significantly hotter than every model of interstellar space had predicted, not by a small margin. The discrepancy was large enough that researchers immediately began questioning whether the models themselves were built on incorrect assumptions. Something in that region was adding energy. Something was heating the plasma in ways that the known physics of interstellar space could not fully account for. The source of that excess heat remains, to this day, an open question. Multiple hypotheses have been advanced. Reconnection of magnetic field lines at the interstellar medium, interactions between neutral atoms and charged particles that generate heat through charge exchange processes. None of them completely resolves the discrepancy. The interstellar medium just outside our solar system is warmer than it should be, and we do not fully understand why. Plasma density told its own disturbing story. Both Voyager probes, as they moved deeper into interstellar space, detected something that no mission had predicted and no ground-based observation had revealed. The density of plasma in the very local interstellar medium was increasing. Slowly, but consistently, the farther from the heliopause they traveled, the denser the interstellar medium became. When Voyager 1 first measured this rise, mission scientists cautioned that it might be a local effect specific to the region that probe happened to cross. When Voyager 2 measured the same increase from a completely different direction, the two probes crossed the heliopause at different points and are now moving through interstellar space on different trajectories. That caution evaporated. The density increase was not local. It was a large-scale feature of the interstellar medium surrounding the entire solar system. Something is piling up out there. Something is compressing the space surrounding our heliosphere from the outside, and it is doing so across a scale that dwarfs anything inside our solar system. If you're not disturbed by that yet, hit like and subscribe, because the next part is what the scientists are struggling to explain in published papers without using language that would alarm the general public. The region in which both Voyager probes are traveling is known in technical literature as the outer Heliosheath. It is the interstellar zone immediately surrounding our solar bubble, the region where interstellar plasma flow is being slowed, compressed, and heated by the presence of the heliosphere pushing back against it. Think of it as the ocean pressing against the hull of a ship, except the ship is our entire solar system, and the ocean is the interstellar medium flowing from the rest of the galaxy. Models of this region, built over decades of theoretical work, predicted that it would be relatively calm, a modest interaction zone. Voyager 2's data tells a different story. Recent analysis of the probe's transmissions found that the outer heliosheath contains compressible disturbances, shock waves, turbulent fluctuations, rapid jumps in plasma density and magnetic field strength that are far more intense and structurally complex than any existing model had suggested. The interstellar medium is not passive. It is alive with motion, pressure, and force that no instrument had ever sampled before, because no instrument had ever been there. In late 2024, NASA made a decision that reflects both the age of the spacecraft and the urgency of what it is finding. The plasma science instrument on Voyager 2, the very instrument that made the heliopause crossing so scientifically valuable, the one that distinguished Voyager 2's data from Voyager 1's incomplete record, was powered down to conserve energy. The plutonium power source aboard the probe loses roughly 4 watts per year, and the spacecraft now runs on so little power that instruments must be switched off one by one to keep the most essential systems alive. With the plasma instrument gone, Voyager 2's ability to directly measure the medium it is moving through has been permanently reduced. What remains are its magnetometer, its cosmic ray detector, and its ability to continue transmitting telemetry home. The window through which we have been reading interstellar space is narrowing, and the data still arriving through that narrowing window continues to surprise. Cosmic rays are one of the few things we can still measure directly from Voyager 2's position. These are high-energy particles accelerated by the deaths of distant stars, supernovae, that travel across the galaxy at nearly the speed of light. Inside the heliosphere, the sun's magnetic field deflects a significant fraction of them, protecting the inner solar system. Voyager 1 measured that the heliosphere blocks more than 70% of galactic cosmic radiation from reaching Earth. That measurement alone was one of the most important findings in the history of space science. But what Voyager 2 is finding as it travels deeper into the interstellar medium is that the cosmic ray environment beyond the heliopause is not uniform. It is structured. The density and energy spectrum of cosmic rays varies in patterns that suggest the medium through which they are traveling has large-scale features, concentrations, voids, directional flows that our maps of the galaxy have never resolved. The galaxy, as seen from inside the heliosphere, looked relatively smooth. From outside it is lumpy, structured, and active in ways that have barely begun to be characterized. And then there is what Voyager 2 has been moving toward. Current calculations place the probe at approximately 143 astronomical units from the Sun, 143 times the distance between Earth and the Sun, or roughly 13 billion miles from home. Models of the interstellar medium suggest that as both Voyager probes continue outward, they will pass through a region of progressively increasing plasma and neutral atom density before eventually reaching the undisturbed interstellar medium far beyond the heliosphere's influence. That region of maximum density, the predicted peak of the compression zone surrounding our solar system, lies somewhere between 200 and 250 astronomical units from the Sun. Voyager 2 has not yet reached it. It is moving toward something its own instruments predicted exists, a wall of compressed interstellar material surrounding our entire solar system. And every reading it sends back tells us that what is waiting there is stranger, denser, and more energetic than any model built before the Voyager probes entered the space between stars had the ability to predict. What does all of this mean in plain language? It means that our solar system does not drift through empty, featureless interstellar space the way a ship moves through a calm sea. It moves through a medium that pushes back, a medium that is compressed and heated at the boundary, a medium that gets denser the farther out you look, a medium that is turbulent, structured, and filled with shock waves traveling from sources we have not fully identified. And Voyager 2, a machine built in the 1970s on technology that would embarrass a modern pocket calculator, is the only instrument humanity has ever placed inside that medium to measure it directly. Its transmissions are not terrifying because they suggest something sinister is waiting in the dark. They are terrifying because they reveal that the dark is not empty, that the quiet is not still, and that the universe outside the small shelter of our solar system is more complex, more powerful, and more unknown than we had the humility to admit before we actually went there. The probe will fall silent within this decade. Its power source will drop below the threshold needed to operate even its most basic systems, and the signal that has been traveling home for almost 50 years will stop. When it does, the direct measurement of interstellar space will end until a new mission is built. A mission that space agencies are already beginning to plan, knowing now what Voyager 2 has proven about what is waiting out there. But before it goes silent, it is still transmitting, still measuring, still sending fragments of a reality that human beings have never touched, never seen, and only recently begun to understand. Every decoded packet of data from that 19-hour-old signal is a piece of information that did not exist in human knowledge before. And every piece suggests the same uncomfortable conclusion. We left the harbor a long time ago. We are only now beginning to understand how vast, how strange, and how alive the ocean actually is. Like and subscribe if you believe that what Voyager 2 is telling us deserves to be heard, because the transmissions are still coming, the data is still being decoded, and the universe outside our door is nothing like we imagined. The difference between what Voyager 2 expected to find and what it actually found is not academic. It is the difference between a universe that is passive and one that is active. Before the Voyager probes entered interstellar space, the prevailing picture was of a solar system drifting serenely through a quiet, mostly uniform interstellar medium, a gentle background against which our sun burned and our planets orbited in relative peace. That picture was not based on nothing. It was built on decades of careful observation from inside the heliosphere, where everything beyond the boundary had to be inferred rather than measured. An inference, no matter how rigorous, is not the same as standing in a place and measuring what is actually there. The Voyager probes stood in the place, and what they measured is a universe that has been pressing against the outside of our solar system all along, turbulent and structured and energetic, generating phenomena that the best theories of the 20th century had not fully anticipated. There is something philosophically unsettling about the timing of all this. Voyager 2 entered interstellar space in 2018. The data from that crossing took years to fully analyze and publish. The implications of that data took further years to absorb, test, and begin to incorporate into revised models of the heliosphere and the surrounding medium. Meanwhile, the probe itself continued to travel outward, its instruments aging, its power fading, its time growing short. By the time humanity fully understands what Voyager 2 has been telling us, the probe will likely be silent. We built a machine, threw it into the unknown, and are still catching up to what it found. That is not a failure. That is what exploration looks like at the edge of everything we know. The transmission from deep space is not a single message. It is a decades-long letter from a frontier that no human being will ever visit, written in plasma wave frequencies and magnetic field readings by a machine that was supposed to last 4 years, and instead changed everything. The decoded transmissions are not an ending. They are an opening line.